Today we're going to talk about functional limits. To do so, we'd like to review the concepts of continuous functions. Let's say that f is a complete ordered field. Recall the given two numbers a and b where a is less than b, the closed interval from a to b is the set of all elements x such that x is greater than or equal to a and x is less than or equal to b. Given a closed interval I, we say that lowercase f is a function if lowercase f of x is defined and unique for each element I, x in our closed interval I. Given a point P in I, we'll say that our lowercase f is continuous at P if, first, L equals f of P is defined and unique, and second, given any epsilon which is positive, we can find a positive delta such that in absolute value f of x minus L is less than epsilon whenever x minus P is less than delta. Otherwise, we'll say that our function lowercase f is discontinuous at P. We'll say that our function lowercase f is continuous on the closed interval I if f is continuous at P for every P in the closed interval I. We can relate all of this with sequences. Say that we have a closed interval I, and let's let lowercase f be a continuous function. Then for each convergent sequence A contained in I, we have the limit as n increases without bound of f of x sub n equals f of p whenever the limit as n increases without bound of x sub n equals p. As a corollary, we have the following statements. Let's say that we have a closed interval I from a to b. Then any subset S of this closed interval is bounded. Moreover, the supremum of S and the infimum of S are both numbers in this closed interval. Let's assume that f is an increasing continuous function. Then f, evaluated at the supremum of capital S, is just the supremum of the set f of capital S. Similarly, let's assume that our function lowercase f is a decreasing continuous function. Then f applied at this element supremum of capital S is the infimum of the set f of capital S. We then had our big three theorems about continuous functions. For all three, let's assume that lowercase f is a continuous function on a closed interval I from a to b. If L is a number between f of a and f of b, then there exists a p in the closed interval such that f of p equals L. That is, f attains all of its intermediate values between f of a and f of b. This, of course, is called the intermediate value theorem. Next, for any continuous function lowercase f on a closed interval I, there exists a lowercase m and an uppercase M such that lowercase m is less than f of x is less than capital M for all x in our closed interval I. That is, every continuous function is bounded on a closed interval. And finally, let's consider our continuous function f on our closed interval I. There exists an element c in our closed interval such that f of x is less than f of c for all x in the closed interval. That is, the function attains its maximum on this closed interval. Similarly, there exists a d in our closed interval such that f of x is greater than or equal to f of d for all x in the closed interval. That is, our function f attains its maximum on the closed interval as well. Now let's assume that f and g are two continuous functions on our closed interval I. Then the sum, f plus g, is also a continuous function. Similarly, the product, f times g, is a continuous function. Moreover, the collection of all continuous functions on our closed interval I actually forms a commutative ring. And as a corollary, every polynomial is a continuous function. There are examples of functions, however, that are discontinuous. Let's define f as that function that takes on the value 1 when x is a rational number, but 0 when x is an irrational number. Then this function f is discontinuous everywhere. Now, let's go over the definitions of functional limits. As before, let's say that I is a closed interval, and let's let lowercase f now be well defined, not necessarily continuous. The following three statements are equivalent for any point in our interval. First, there's the epsilon delta criterion. Given a positive epsilon, we can find a positive delta such that in absolute value, f of x minus L is less than epsilon, whenever in absolute value x minus p is less than delta. However, we also need x minus p to not equal 0. Next, there's the topological criteria. For every open interval, V's open neighborhood, V sub epsilon of L, which consists of those real numbers y, such that in absolute value, y minus L is less than epsilon, there exists an open neighborhood V sub delta of P, such that f of x is contained in V sub epsilon of L, whenever x is contained in V sub delta of P, but x different from P. And finally, we have the sequential criteria. We have the limit as n increases without bound of f of x sub n equals L for all sequences A contained in I, such that x sub n does not equal to P, and the limit as n increases without bound of x sub n equals P. Any of these three equivalent statements, that is the epsilon delta criterion, the topological criterion, or the sequential criterion, if any one of these holds, will say that the limit as x approaches p of f of x equals L. Later, we're going to use this to define what it means to be continuous in a slightly different way. Let's present the proof. First, let's assume that given a positive epsilon, we can find a positive delta such that f of x minus L is less than epsilon whenever x minus p is between 0 and delta. With this epsilon, let's consider the open neighborhood V sub epsilon of L that contains L. And let's assume that x is contained in the neighborhood V sub delta of p, but x does not equal to p. Then, of course, this means that x minus p is between delta and 0, so by our assumption, f of x minus L is less than epsilon. But then this means that y equals f of x must be an element of our open neighborhood V sub epsilon of L. Now let's show 2 implies 3. Let's assume that for every V sub epsilon of L containing L, there exists a neighborhood V sub delta of P such that f of x is an element of V sub epsilon of L whenever x is an element of V sub delta of P, yet x is different from P. Now let's choose any sequence capital A contained in our closed interval I such that x sub n does not equal to P, yet the limit as n increases without bound of x sub n equals P. Let's let epsilon positive be given, and let's choose delta positive as in the assumption. Since the limit as of x sub n equals p, we can find some index n sub 0 such that xn minus p is less than delta whenever n is greater than n0. But then x sub n is an element of the neighborhood v sub delta of p, so the image f of x sub n is an element of the neighborhood v sub epsilon of L. But then this means, in absolute value, f of x sub n minus L should be less than epsilon whenever n is greater than n0. Of course, by definition, this means that f of x sub n equals L. Now let's do the last part. 3 implies 1. Let's assume that we have the limit of f of xn equals L for all sequences contained in I, such that x sub n does not equal to p, yet the limit of the x sub n's equals p. We need to prove that given a positive epsilon, we can find a positive delta such that f of x minus L is less than epsilon whenever x minus p is between 0 and delta. Let's assume by way of contradiction that this is not true. That is, we can find some epsilon sub 0 such that f of x minus L is greater than or equal to epsilon 0 whenever x minus p is between 0 and delta. And this should be true for any delta. Now, because p is between a and b, let's choose delta sub n to be the max of p minus b, or p minus a, all divided by 2 to the n, where n here is 0, 1, 2, and so forth. We're going to define x sub n as p plus delta n over 2, so that x sub n is in the open neighborhood v sub delta n of p, and is also in the open neighborhood in the closed interval I, yet x sub n does not equal p. Then we have here a sequence of x sub n's that's contained in our closed interval I. X sub n does not equal to p, and the limit of the x sub n's does equal p. But by assumption, the limit for the f of x sub n's equals L, meaning given any epsilon, in particular epsilon 0, we can find an index n0 such that f of x sub n minus L is less than epsilon 0 whenever n is greater than n0. But of course, this here is a contradiction. We'll end today with two results whose proofs will be left for the breakout rooms in class. Let's say that I is a closed interval, and let's say that f and g are two well-defined functions such that the limit as x tends to p of f of x is L, and the limit as x tends to p of g of x equals m. We have the following two limits. For any scalars alpha and beta, the limit as x tends to p of alpha times f of x plus beta times g of x is just alpha times L plus beta times m. Similarly, the limit as x tends to p of f of x times g of x is L times p. Finally, we have a way to see when a limit does not exist. This is the so-called divergence criteria. Let's say that we have a function defined in a closed interval from a to b. And let's take a look at two sequences, capital A in terms of x sub n's and capital B in terms of y sub n's, such that the limit of the x sub n's equals the limit of the y sub n's equals a common point p, yet the limit of the f of x sub n's does not equal the limit of the f of y sub n's. Then the limit as x tends to p of f of x does not exist. Thanks very much for listening.